All right, everyone, welcome to Ops Lecture 13. We've had 13 lectures, oh my goodness. This is our last lecture. We're not gonna have any more lectures. We're probably gonna have work session and then your capstone is due at the end of this month. Can you believe it's May? I cannot. All right, so last Friday, the half capstone was due and then I know there are some of you who haven't gotten checked off, so you can still get checked off for that, but do talk to us. And we've been having some battery issues with the battery in the kit because that battery happens to be very cheap. So we'll talk more about that today. Full capstone is just your half capstone plus some autopilot mode. So we're going to talk about autopilot modes, different modes that you can implement, and the ultrasonic sensor that you're going to use to do this, and also PID control. All right, so in terms of deadlines, we already crossed off these two deadlines. So May 29th, Saturday, 11:59 p.m. is when everything is due. I know we've had like only soft deadlines, but this one is actually a hard deadline. So please do make sure to get your stuff turned in by then, because you will not be able to submit anything additional afterwards. Because May 30th, Sunday, is our competition. We'll be showing off some of the coolest submissions for the competition categories and giving out prizes. If you have cool prize ideas, you can still let us know in this link over here up until probably end of next week. All right, so competition categories. We have 3 categories that you can enter for. First one is best autopilot. So we're going to talk about different, ways to implement or think about autopilot, and the most interesting and complex, or just the best most well implemented autopilot function will win this category. And then we also have best interface for most friendly and functional remote control interface, most creative for best integration of additional components that are fun. All right, so we hope you have fun with the capstone project. The requirements are pretty simple in order to allow you to go off and be creative once you have those basic requirements done. And for this full capstone, we're going to have you guys check yourselves off, or just submit answers for the checkoff questions, as well as your code and a video. Right. And then if you do want to enter for the competition, there's a separate submission form for the competition. So the final checkup form is required, competition form not required, but highly encouraged. All right.
All right, so as many of you sadly know, there are a lot of issues with the battery in the kit. I don't think it worked for anyone, so that's pretty sad. So one thing you could do is buy a battery. That works well. It doesn't last an extremely long time. So if you do buy a battery, we encourage you to put it on a limited speed. That will just increase its lifetime and allow you to use it longer, so that way you don't have to buy a different battery every day. As we've told you before, you're going to want to prototype and debug while on the USB supply, so that way you are not wasting a bunch of batteries unless you have a lot of batteries on hand to waste. And then one of the issues that might happen going from prototyping on the USB to actually using a battery is that you're going to have to recalibrate the constants you use for PID. We're going to talk about that in a little bit, but it's going to be a little bit of extra work you have to do when you transition to the battery. You're not going to be able to just, plug in the battery and be done with it.
Yes, but it is very cool to have a fresh new battery attached to your car. It'll go a lot faster than whatever the kit battery gave you, because I don't know what's up with those batteries, but they're just not it. But yeah, so if you can and are interested, we do recommend that you get a battery and test it out if you want to. All right, so the full capstone, we have 2 autopilot modes. You want to talk about the first one, Ryder?
Yes, so the first one is going to be the wall following car. This one's for if you made your board like long way, like if it's a limo, you can see in the picture there. So what you're gonna do with that is you're gonna put the ultrasonic sensor on the side of it. It doesn't really matter which side. And then what you're gonna do is travel along the wall. So your sensor is now facing the wall, and you're gonna track along the wall until you get to the corner of the wall, in which an IR pair in the very front of your car will detect the wall, turn 90 degrees, and then repeat the same process.
So basically, all you have to do to go from half to full is implement a new button, make a new button that tells the car to go autopilot until you press another button that tells it to go otherwise. I'm just seeing Caleb's face in Brenda's background is throwing me off. Okay, so the second option you have is a hand following or the object following autopilot mode. So this will work better if you had your board horizontally, the fat way. So you'll have the ultrasonic sensor in the front like this, and probably be able to mount some battery on here. So then what you're gonna do is you're gonna move an object in front of the car, and then your car will follow it. And then if you move it back, it'll follow it backwards. All right, so we're gonna have you guys use the ultrasonic sensor for this project. These work a lot better than the IR sensors. I know our IR sensors and IR pairs have been broken, but we do have a note on that in our spec if you do want to implement multiple sensor things. So what you have to do with the ultrasonic sensor, the idea is pretty similar to IR sensors. They emit ultrasonic pulses, and then they travel through the air. And then when there's an object, if there's an object within the range, it gets reflected back, and then the sensor reads it, and then you can use the time that passed between the pulses going out to when when they got reflected back in order to calculate the distance. So the trig pin, so there are 4 pins on the ultrasonic sensor, VCC and ground. You already know at this point, they're just VCC and ground. Do connect VCC to 5 volts. And then trig pin, you have to write a short pulse to make the sensor start, tell the sensor to emit these ultrasonic pulses. And then once that happens, this echo pin will start, and then when the pulse is reflected back, it'll go down back to low. So then you can use the width of the pulse at the echo pin to measure the distance of your object. I know that was not the best way to put it. It's a lot clearer in the spec because we have it written down. And in order to measure the width of your pulse, we're going to use the pulse in function. That's a built-in function. A lot more on this as well in the spec. So do read the spec.
Okay, now we're going to get into PID. So really quick, the idea of PID is sort of you're taking into account error and you're looking at it at the error like straight up. That's the proportional term. So you're scaling the error. There's a derivative term and an integral term. So this part, we're going to talk about how we get the actual derivative and integral of the error. So as you can imagine, you might have a standard distance you want your sensor away from something. And then however far away you are from that distance will be your error, right? So that's a pretty simple measurement to take. You know, you just see how far you are, you subtract off where you want to be. That's your error and distance. But the derivative and integral of the error might be trickier to do. So one function that's useful is this function millis that returns to you the time in milliseconds that's the Arduino has been running since it's been reset or since you uploaded your code. You can use this in successive loops to calculate the time difference between the 2 loops. So you run it once, record the time, run it again. You have a new time, subtract them. That's how much time has passed. So here we have the error correction term. Like I said, let's talk about how we actually calculate the derivative of the error first. So we're not actually calculating derivatives or integrals because that's complicated and would take a library probably, I don't know. But what we can do is since these time intervals are going to be very short, we could kind of just average out the slope and integral. So what we're doing here for the derivative is we're looking at our current error, we're subtracting off our previous error and dividing it by the time elapsed. So that makes a sort of a linear model of the derivative. And then for the integral, this is cumulative, so that's why you need to have the integral is equal to the integral plus time elapsed plus the current error. So that's kind of like the Riemann sum, if you guys remember that. So the time elapsed is the width of the amount of time since the last error, and then the height of it would be the current error. And then Kp, Kd, and Ki, those values are what you're going to be changing. So the three error terms, those you're going to be calculating in your code. Kp, Kd, and Ki is what you're testing to see which works better or worse. And that's kind of a trial and error process. But there are ways you can sort of be strategic about how you pick these values.
Yeah, so these values, before you write anything to your motors, you want to make sure you're writing reasonable values. So you want to use the serial monitor to observe your values and just be a little bit smarter about it. And that way you can avoid having to upload your code like 1,000 times. Yeah.
Okay, and then some of this is a little bit of review. So we did talk about this in one of our lectures last quarter, but it's okay if you don't remember it. So the whole idea of PID comes from the idea of a feedback loop. So you have a desired state. It goes through these sort of controllers that calculate the different types of error terms. And then the error is calculated again and fed back, and this is repeated until it should stabilize on a place you want. So our goal is to make that error equal to 0 as quickly as possible, and that's where we get to the distance we want. So let's quickly talk about the proportional term. So this would be Kp. So this is based on, so if you remember from the earlier equation, it was just Kp times the error. So this is completely based on position, right? So if you look at this blue square here, what's happening is that if the blue square is on the left, the error is then, you could think of it as like positive or negative. The Kp term is multiplying it, and therefore it is correcting to the right. And once it passes the line, the error is the other way, so it pushes it back. You can see that right here, Kp is 0.1. If the Kp was something higher, it might overshoot the line even more because it's sort of scaling the proportional error by that much. If it was less, it would overshoot it less. But if you notice, it still has this sort of oscillatory behavior where it doesn't quite settle correctly. So that's why we have to introduce another term to account for that. And that's where the derivative term comes in super useful to us. So what this does is the derivative monitors the change in the error, right? So it's the slope of the error. As your square approaches this line, the error is getting less and less, right? So your need to correct should go down. And if you look at these other colors, that's what it's kind of doing. So the pink one has a KD of 1. So as you see, it doesn't overshoot by as much. Then as we increase it even more, it's able to slow it down even more, essentially, right? And then we have different terms like underdamped, critically damped, overdamped. I'm sure a lot of you guys have heard of that. That's going to be one of the main objectives of this project, is to try and find the best KD, that kind of NKP combination that gets you to settle to the distance you want as quickly as possible. All right.
That's about it for PID control and PID constants. In terms of deadlines, we have, May 29th deadline. This is the last deadline you'll ever have. Please, please, nothing past midnight, please. And this is also the last spec you'll see from us. So just to be clear, there's no need to come to the lab for a checkup, but we will be there if you need help or just want to hang out with us. And then there will be no more lectures, just work sessions or just hangout sessions for those of you who are interested. Right. Was there anything else, Ryder?
No, just don't wait till the last week to do this one, You're gonna end up late, and we're not gonna, even if you ask for an extension, we can't extend the deadline. So This really is a hard deadline. Get started on it early.
Yep, and do pay attention to the spec. It goes over pretty much everything you need to know. So if you read, you won't have too much trouble. That's our hope. All right. So thank you for joining OFS for almost a year. It's been a pleasure of mine to talk to you guys over these 13 lectures and lab sessions. Any final words, Ryder?
Yeah, I guess I want to just copy what Taylor said. It really has been a pleasure working with all of you this year. I hope you guys, all go on to do more projects. You stay involved in IEEE and all that. And yeah, thanks.
All right, thank you. I am going to stop the recording now.